Chapter 9. Risk Management. Introduction. Pull the throttle back. Lenore, a certificated flight instructor, CFI, ordered the student, Jennifer, as the revolutions per minute, RPM, climbed past 2,000 on engine startup. I did. Both Jennifer and Lenore grabbed the mixture and pulled. The engine went from a deafening roar to silence. They looked at each other. What happened? Asked Jennifer. I don't know. Let's check the engine, Lenore said. 10 minutes later, they had removed the cowling from the Cessna 152. A quick engine check gave them the answer. The throttle rod end was not connected to the carburetor arm. No bolt, no nut, just air between the rod end and the arm. Jennifer looked at Lenore. What if this happened in flight? What I want to know, Lenore said, is how this happened at all. The annual inspection was signed off yesterday. The previous day, the annual inspection had been signed off after a lengthy inspection by a local facility. Several mechanics had been involved in the inspection, including the owner/student who had installed a headliner. The mechanic with the inspection authorization, IA, who signed off the annual, was supervising several annuals, so most of the maintenance was performed by other mechanics. After the inspection, the engine had been run up according to the usual post-inspection procedures. The student and instructor had flown the airplane for a half-hour familiarization flight. The next day's engine start resulted in a runaway engine, with the apparent cause due to the lack of the throttle rod end hardware being safetied. 3 deficient areas in this annual inspection were identified by a round-table discussion group of aircraft and power plant, A&P, mechanics, and the student. These areas were lack of responsibility, checklist misuse, complacency. Lack of responsibility. No one took responsibility for the entire inspection. The chances of something being overlooked increase with an increase in the number of mechanics involved in an inspection. The responsible person is removed from the actual procedure. The student remembers hearing the IA ask one of the engine mechanics about the throttle. However, the question was vague, the answer was vague, and the rod end was not safetied. Checklist misuse. All checklists have a line item regarding inspection of the engine controls for rigging and safety. Perhaps the throttle rod end had been disconnected for maintenance after the IA had signed off the control inspection. In that case, a discrepancy should have been entered onto the discrepancy sheet stating reconnect and safety throttle rod end. Complacency. An insidious and hard-to-identify attitude. Each of the mechanics involved in the incident thought someone else had inspected the throttle rod end. The IA signed off the annual inspection because he had either asked the mechanics about the items on the checklist or, in his frequent visits to the airplane, had inspected the various items himself and decided that was good enough. Complacency crippled the mechanic's quality of work by removing any thoughts of double-checking each other's work. While a definite answer to the question of what happened remains a matter of speculation, professional mechanics should heed warning signs of potential problems. The combination of a lengthy inspection, numerous technicians, an overworked supervisor, a poor checklist, and vague communication should raise a red flag of caution. Although the ultimate responsibility for the safety of any flight rests with the pilot in command, PIC, it is not unreasonable for the PIC to assume that mechanics also take their responsibilities seriously. This scenario underscores the need for safety risk management at all levels of aviation. Safety risk management, a formal system of hazard identification and analysis, is essential for keeping risk at acceptable levels. Part of this process is selecting the appropriate controls to mitigate the risk of the identified hazard. The primary objective of risk management is accident prevention, which is achieved by proactively identifying, assessing, and eliminating or controlling safety-related hazards to acceptable levels. This chapter discusses safety risk management in the aviation community, looking at it as preemptive rather than reactive. The principles of risk management and the tools for teaching risk management in the flight training environment are addressed in Chapter 8, Techniques of Flight Instruction. Defining risk management. Risk is defined as the probability and possible severity of accident or loss from exposure to various hazards, including injury to people and loss of resources. Figure 9-1. All Federal Aviation Administration (FAA) operations in the United States involve risk and require decisions that include risk assessment and risk management. Risk management, a formalized way of thinking about these topics, is the logical process of weighing the potential costs of risks against the possible benefits of allowing these risks to stand uncontrolled. Risk management is a decision-making process designed to identify hazards systematically, assess degree of risk, and determine the best course of action. Key terms are hazard, a present condition, event, object, or circumstance that could lead to or contribute to an unplanned or undesired event, such as an accident. It is a source of danger. For example, a nick in the propeller represents a hazard. Risk, the future impact of a hazard that is not controlled or eliminated. It is the possibility of loss or injury. The level of risk is measured by the number of people or resources affected, exposure, the extent of possible loss, severity, and the likelihood of loss, probability. Safety, freedom from those conditions that can cause death, injury, occupational illness, or damage to or loss of equipment or property, or damage to the environment. Note that absolute safety is not possible because complete freedom from all hazardous conditions is not possible. Therefore, safety is a relative term that implies a level of risk that is both perceived and accepted. Figure 9-1, text. Types of risk. Total risk, the sum of identified and unidentified risks. Identified risk, risk which has been determined through various analysis techniques. The first task of system safety is to identify, within practical limitations, all possible risks. Unidentified risk, risk not yet identified. Some unidentified risks are subsequently identified when a mishap occurs. Some risk is never known. Unacceptable risk, risk which cannot be tolerated by the managing activity. It is a subset of identified risk that must be eliminated or controlled. Acceptable risk. Acceptable risk is the part of identified risk that is allowed to persist without further engineering or management action. Making this decision is a difficult yet necessary responsibility of the managing activity. This decision is made with full knowledge that it is the user who is exposed to the risk. Residual risk. Residual risk is the risk left over after system safety efforts have been fully employed. It is not necessarily the same as acceptable risk. Residual risk is the sum of acceptable risk and unidentified risk. This is the total risk passed on to the user. End of Figure 9-1 text. Principles of risk management. Accept no unnecessary risk. Unnecessary risk is that which carries no commensurate returns in terms of benefits or opportunities. Everything involves risk. The most logical choices for accomplishing an operation are those that meet all requirements with a minimum acceptable risk. The corollary to this axiom is accept necessary risk required to complete the operation or task successfully. Flying is impossible without risk, but unnecessary risk comes without a corresponding return. If flying a new airplane for the first time, a CFI might determine that the risk of making the flight in low instrument flight rules, IFR, conditions is unnecessary. Make risk decisions at the appropriate level. Anyone can make a risk decision. However, the appropriate decision maker is the person who can develop and implement risk controls. The decision maker must be authorized to accept levels of risk typical of the planned operation. In a single pilot situation, the pilot makes the decision to accept certain levels of risk. In the maintenance facility, an aviation maintenance technician, AMT, may need to elevate decisions to the next level in the chain of management upon determining that those controls available to him or her will not reduce residual risk to an acceptable level. Accept risk when benefits outweigh the costs. All identified benefits should be compared against all identified costs. Even high-risk endeavors may be undertaken when there is clear knowledge that the sum of the benefits exceeds the sum of the costs. For example, in any flying activity, it is necessary to accept some degree of risk. A day of good weather, for example, is a much better time to fly an unfamiliar airplane for the first time than a day with low instrument flight rules, IFR conditions. Integrate risk management into planning at all levels. Risks are more easily assessed and managed in the planning stages of an operation. The later changes are made in the process of planning and executing an operation, the more expensive and time-consuming they become. Because risk is an unavoidable part of every flight, safety requires the use of appropriate and effective risk management, not just in the pre-flight planning stage, but in all stages of the flight. Risk management process. Risk management is a simple process which identifies operational hazards and takes reasonable measures to reduce risk to personnel, equipment, and the mission. Step 1. Identify the hazard. A hazard is defined as any real or potential condition that can cause degradation, injury, illness, death, or damage to, or loss of equipment or property. Experience, common sense, and specific analytical tools help identify risks. Step 2. Assess the risk. The assessment step is the application of quantitative and qualitative measures to determine the level of risk associated with specific hazards. This process defines the probability and severity of an accident that could result from the hazards based upon the exposure of humans or assets to the hazards. Step 3. Analyze risk control measures. Investigate specific strategies and tools that reduce, mitigate, or eliminate the risk. All risks have two components. 1. Probability of occurrence. 2. Severity of the hazard. Effective control measures reduce or eliminate at least one of these. The analysis must take into account the overall costs and benefits of remedial actions, providing alternative choices if possible. Step 4. Make control decisions. Identify the appropriate decision maker. That decision maker must choose the best control or combination of controls based on the analysis of steps 1 and 2. Step 5. Implement risk controls. A plan for applying the selected controls must be formulated. The time, materials, and personnel needed to put these measures in place must be provided. Step 6. Supervise and review. Once controls are in place, the process must be re-evaluated periodically to ensure their effectiveness. People at every level must fulfill their respective roles to assure the controls are maintained over time. The risk management process continues throughout the life cycle of the system, mission, or activity. Implementing the risk management process. To derive maximum benefit from this powerful tool, it must be used properly. The following principles are essential. Apply the steps in sequence. Each step is a building block for the next and must be completed before proceeding to the next. If a hazard identification step is interrupted to focus on the control of a particular hazard, more important hazards may be overlooked. Until all hazards are identified, the remainder of the process is not effective. Maintain a balance in the process. All steps are important. Allocate the time and resources to perform all. Apply the process in a cycle. The supervise and review step should include a brand new look at the operation being analyzed to see whether new hazards can be identified. Involve people in the process. Ensure that risk controls are mission supportive, and the people who must do the work see them as positive actions. The people who are actually exposed to risks usually know best what works and what does not. Level of risk. The level of risk posed by a given hazard is measured in terms of severity, extent of the possible loss, probability, likelihood that a hazard will cause a loss. Assessing risk. Assessment of risk is an important part of good risk management. For example, The hazard of a nick in the propeller poses a risk only if the airplane is flown. If the damaged prop is exposed to the constant vibration of normal engine operation, there is a high risk that it could fracture and cause catastrophic damage to the engine and/or airframe and the passengers. Every flight has hazards and some level of risks associated with it. It is critical that pilots, and especially students, are able to differentiate in advance between a low-risk flight and a high-risk flight, and then establish a review process and develop risk mitigation strategies to address flights throughout that range. For the single pilot, assessing risk is not as simple as it sounds. For example, the pilot acts as his or her own quality control in making decisions. If a fatigued pilot who has flown 16 hours is asked if he or she is too tired to continue flying, the answer may be no. Most pilots are goal-oriented, and when asked to accept a flight, there is a tendency to deny personal limitations while adding weight to issues not germane to the mission. For example, pilots of helicopter emergency services, EMS, have been known to make flight decisions that add significant weight to the patient's welfare. These pilots add weight to intangible factors, the patient in this case, and fail to appropriately quantify actual hazards such as fatigue or weather when making flight decisions. The single pilot, who has no other crew member for consultation, must wrestle with the intangible factors that draw one into a hazardous position. Therefore, he or she has greater vulnerability than a full crew. Examining National Transportation Safety Board, NTSB, reports and other accident research can help a pilot learn to assess risk more effectively. For example, the accident rate during night VFR decreases by nearly 50% once a pilot obtains 100 hours and continues to decrease until the 1,000-hour level. The data suggest that for the first 500 hours, pilots flying VFR at night might want to establish higher personal limitations than are required by the regulations and, if applicable, apply instrument flying skills to this environment. Several risk assessment models are available to assist in the process of assessing risk. The models, all taking slightly different approaches, seek a common goal of assessing risk in an objective manner. The most basic tool is the risk matrix, Figure 9-2. It assesses two items: the likelihood of an event occurring and the consequences of that event. Likelihood of an event. Likelihood is nothing more than taking a situation and determining the probability of its occurrence. It is rated as probable, occasional, remote, or improbable. For example, a pilot is flying from point A to point B, 50 miles, in marginal visual flight rules, MVFR, conditions. The likelihood of encountering potential instrument meteorological conditions, IMC, is the first question the pilot needs to answer. The experiences of other pilots, coupled with the forecast, might cause the pilot to assign occasional to determine the probability of encountering IMC. The following are guidelines for making assignments. Probable. An event will occur several times. Occasional. An event will probably occur sometime. Remote. An event is unlikely to occur, but is possible. Improbable. An event is highly unlikely to occur. Severity of an event. The next element is the severity or consequences of a pilot's actions. It can relate to injury and/or damage. If the individual in the example above is not an Instrument Flight Rules IFR pilot, what are the consequences of encountering inadvertent IMC? In this case, because the pilot is not IFR rated, the consequences are catastrophic. The following are guidelines for this assignment. Catastrophic. Results in fatalities, total loss. Critical. Severe injury, major damage. Marginal. Minor injury, minor damage. Negligible. Less than minor injury, less than minor system damage. Simply connecting the two factors as shown in Figure 9-2 indicates the risk is high and the pilot must either not fly or fly only after finding ways to mitigate, eliminate, or control the risk. Mitigating risk. Risk assessment is only part of the equation. After determining the level of risk, the pilot needs to mitigate the risk. For example, the pilot flying from point A to point B, 50 miles, in MVFR conditions has several ways to reduce risk. Wait for the weather to improve to good visual flight rules, VFR conditions. Take a pilot who is rated as an IFR pilot. Delay the flight. Cancel the flight. Drive. I'm safe, IMSAFE checklist. One of the best ways that single pilots can mitigate risk is to use the I'm safe checklist, figure 9-3, to determine physical and mental readiness for flying. 1. Illness. Am I sick? Illness is an obvious pilot risk. 2. Medication. Am I taking any medicines that might affect my judgment or make me drowsy? 3. Stress. Am I under psychological pressure from the job? Do I have money, health, or family problems? Stress causes concentration and performance problems. While the regulations list medical conditions that require grounding, stress is not among them. The pilot should consider the effects of stress on performance. 4. Alcohol. Have I been drinking within 8 hours? Within 24 hours? As little as 1 ounce of liquor, 1 bottle of beer, or 4 ounces of wine can impair flying skills. Alcohol also renders a pilot more susceptible to disorientation and hypoxia. 5. Fatigue. Am I tired and not adequately rested? Fatigue continues to be one of the most insidious hazards to flight safety, as it may not be apparent to a pilot until serious errors are made. 6. Eating. Have I eaten enough of the proper foods to keep adequately nourished during the entire flight? The PAVE checklist. Another way to mitigate risk is to perceive hazards. By incorporating the PAVE checklist into all stages of flight planning, the pilot divides the risks of flight into 4 categories. P. Pilot in command, PIC. A. Aircraft. V. Environment. And E. External pressures, PAVE, which form part of the pilot's decision-making process. With the PAVE checklist, pilots have a simple way to remember each category to examine for risk prior to each flight. Once a pilot identifies the risk of a flight, he or she needs to decide whether the risk or combination of risks can be managed safely and successfully. If not, make the decision to cancel the flight. If the pilot decides to continue with the flight, he or she should develop strategies to mitigate the risks. One way a pilot can control the risks is to set personal minimums for items in each risk category. These are limits unique to that individual pilot's current level of experience and proficiency. For example, the aircraft may have a maximum crosswind component of 15 knots listed in the Aircraft Flight Manual, AFM, and the pilot has experience with 10 knots of direct crosswind. It could be unsafe to exceed 10 knots crosswind component without additional training. Therefore, the 10 knots crosswind experience level is that pilot's personal limitation until additional training with a certificated flight instructor, CFI, provides the pilot with additional experience for flying in crosswinds that exceed 10 knots. One of the most important concepts that safe pilots understand is the difference between what is legal in terms of the regulations and what is smart or safe in terms of pilot experience and proficiency. P equals pilot in command, PIC. The pilot is one of the risk factors in a flight. The pilot must ask, am I ready for this trip? In terms of experience, currency, physical and emotional conditions, the I'm safe checklist, combined with proficiency, recency, and currency, provides the answers. A equals aircraft. What limitations will an aircraft impose upon the trip? Ask the following questions. Is this the right aircraft for the flight? Am I familiar with and current in this aircraft? Aircraft performance figures and the AFM are based on a brand new aircraft flown by a professional test pilot. Keep that in mind while assessing personal and aircraft performance. Is this aircraft equipped for the flight? Instruments, lights, navigation, and communication equipment adequate? Can this aircraft use the runways available for the trip with an adequate margin of safety under the conditions to be flown? Can this aircraft carry the planned load? Can this aircraft operate at the altitudes needed for the trip? Does this aircraft have sufficient fuel capacity with reserves for trip legs planned? Does the fuel quantity delivered match the fuel quantity ordered? V equals environment. Weather is a major environmental consideration. Earlier, it was suggested pilots set their own personal minimums, especially when it comes to weather. As pilots evaluate the weather for a particular flight, they should consider the following. What are the current ceiling and visibility? In mountainous terrain, consider having higher minimums for ceiling and visibility, particularly if the terrain is unfamiliar. Consider the possibility that the weather may be different than forecast. Have alternative plans and be ready and willing to divert should an unexpected change occur. Consider the winds at the airports being used and the strength of the crosswind component. If flying in mountainous terrain, consider whether there are strong winds aloft. Strong winds in mountainous terrain can cause severe turbulence and downdrafts and can be very hazardous for aircraft even when there is no other significant weather. Are there any thunderstorms present or forecast? If there are clouds, is there any icing, current, or forecast? What is the temperature dew point spread and the current temperature at altitude? Can descent be made safely all along the route? If icing conditions are encountered, is the pilot experienced at operating the aircraft's de-icing or anti-icing equipment? Is this equipment in good condition and functional? For what icing conditions is the aircraft rated, if any? Evaluation of terrain is another important component of analyzing the flight environment. To avoid terrain and obstacles, especially at night or in low visibility, determine safe altitudes in advance by using altitudes shown on VFR and IFR charts during pre-flight planning. Use maximum elevation figures, MEFs, and other easily obtainable data to minimize chances of an in-flight collision with terrain or obstacles. Airport considerations include what lights are available at the destination and alternate airports. VASI/PAPI or ILS glide slope guidance? Is the terminal airport equipped with them? Are they working? Will the pilot need to use the radio to activate the airport lights? Check the notices to airmen, NOTAMs, NOTAMs, for closed runways or airports. Look for runway or beacon lights out, nearby towers, etc. Choose the flight route wisely. An engine failure gives the nearby airports and terrain supreme importance. Are there shorter or obstructed fields at the destination and or alternate airports? Airspace considerations include if the trip is over remote areas, are appropriate clothing, water, and survival gear on board in the event of a forced landing? If the trip includes flying over water or unpopulated areas with a chance of losing visual reference to the horizon, the pilot must be current, equipped, and qualified to fly IFR. Check the airspace and temporary flight restrictions, TFRs, along the route of flight. Night flying requires special consideration. If the trip includes flying at night over water or unpopulated areas with a chance of losing visual reference to the horizon, the pilot must be prepared to fly IFR. Will the flight conditions allow a safe emergency landing at night? Pre-flight, all aircraft lights, interior and exterior, for night flight. Carry at least 2 flashlights, one for exterior pre-flight, and a smaller one that can be dimmed and kept nearby. E equals external pressures. External pressures are influences external to the flight that create a sense of pressure to complete a flight, often at the expense of safety. Factors that can be external pressures include the following: someone waiting at the airport for the flight's arrival, a passenger the pilot does not want to disappoint, the desire to demonstrate pilot qualifications, the desire to impress someone. Probably the two most dangerous words in aviation are "watch this." The desire to satisfy a specific personal goal. Get home-itis, get there-itis, and let's go-itis. The pilot's general goal completion orientation. Emotional pressure associated with acknowledging that skill and experience levels may be lower than a pilot would like them to be. Pride can be a powerful external factor. Management of external pressure is the single most important key to risk management, because it is the one risk factor category that can cause a pilot to ignore all the other risk factors. External pressures put time-related pressure on the pilot and figure into a majority of accidents. The use of Personal Standard Operating Procedures, SOPs, is one way to manage external pressures. The goal is to supply a release for the external pressures of a flight. These procedures include, but are not limited to, allow time on a trip for an extra fuel stop or to make an unexpected landing because of weather. Have alternate plans for a late arrival or make backup airline reservations for must-be-there trips. For really important trips, plan to leave early enough so that there would still be time to drive to the destination. Advise those who are waiting at the destination that the arrival may be delayed. Know how to notify them when delays are encountered. Manage passenger expectations. Make sure passengers know that they might not arrive on a firm schedule, and if they must arrive at a certain time, they should make alternative plans. Eliminate pressure to return home, even on a casual day flight, by carrying a small overnight kit containing prescriptions, contact lens solutions, toiletries, or other necessities on every flight. The key to managing external pressure is to be ready for and accept delays. Remember that people get delayed when traveling on airlines, driving a car, or taking a bus. The pilot's goal is to manage risk, not create hazards. During each flight, decisions must be made regarding events involving interactions between the four risk elements: PIC, aircraft, environment, and external pressures. The decision-making process involves an evaluation of each of these risk elements to achieve an accurate perception of the flight situation. Figure 9-4. 3P model for pilots. Risk management is a decision-making process designed to perceive hazards systematically, assess the degree of risk associated with the hazard, and determine the best course of action. See Appendix F. For example, the Perceive, Process, Perform 3P model for aeronautical decision-making, ADM, offers a simple, practical, and structured way for pilots to manage risk. Figure 9-5. To use the 3P model, the pilot perceives the given set of circumstances for a flight, processes by evaluating the impact of those circumstances on flight safety, performs by implementing the best course of action. In the first step, the goal is to develop situational awareness by perceiving hazards, which are present events, objects, or circumstances that could contribute to an undesired future event. In this step, the pilot systematically identifies and lists hazards associated with all aspects of the flight: pilot, aircraft, environment, and external pressures. It is important to consider how individual hazards might combine. Consider, for example, the hazard that arises when a new instrument pilot with no experience in actual instrument conditions wants to make a cross-country flight to an airport with low ceilings in order to attend an important business meeting. In the second step, the goal is to process this information to determine whether the identified hazards constitute risk, which is defined as the future impact of a hazard that is not controlled or eliminated. The degree of risk posed by a given hazard can be measured in terms of exposure, number of people or resources affected, severity, extent of possible loss, and probability, the likelihood that a hazard will cause a loss. If the hazard is low ceilings, for example, the level of risk depends on a number of other factors, such as pilot training and experience, aircraft equipment, and fuel capacity. In the third step, the goal is to perform by taking action to eliminate hazards or mitigate risk, and then continuously evaluate the outcome of this action. With the example of low ceilings at destination, for instance, the pilot can perform good ADM by selecting a suitable alternate, knowing where to find good weather, and carrying sufficient fuel to reach it. This course of action would mitigate the risk. The pilot also has the option to eliminate it entirely by waiting for better weather. Once the pilot has completed the 3P decision process and selected a course of action, the process begins again because the set of circumstances brought about by the course of action requires analysis. The decision-making process is a continuous loop of perceiving, processing, and performing. It is never too early to start teaching students about risk management. Using the 3P model gives CFIs a tool to teach them a structured, efficient, and systematic way to identify hazards, assess risk, and implement effective risk controls. Practicing risk management needs to be as automatic in general aviation, GA, flying, as basic aircraft control. Consider making the 3P discussion a standard feature of the pre-flight discussion. As is true for other flying skills, risk management habits are best developed through repetition and consistent adherence to specific procedures. A hazard list for aviation technicians. AMTs should learn about risk management early in training also. Instructors tasked with integrating risk management into instruction can turn to hazard assessments that identify the safety risks associated with the facility being used, the tools used in the procedure, and/or the job being performed. The process for identifying hazards can be accomplished through the use of checklists, lessons learned, compliance inspections/audits, accidents/near misses, regulatory developments, and brainstorming sessions. For example, aviation accident reports from the National Transportation Safety Board, NTSB, can be used to generate discussions pertaining to faulty maintenance that led to aircraft accidents. All available sources should be used for identifying, characterizing, and controlling safety risks. The 3P model can also be adapted for use in a non-flight environment, such as a maintenance facility. For example, the AMT perceives a hazard, processes its impact on shop or personnel safety, and then performs by implementing the best course of action to mitigate the perceived risk. Pilot self-assessment. Setting personal minimums is an important step in mitigating risk, and safe pilots know how to properly self-assess. For example, in the opening scenario, the aircraft Mary plans to fly may have a maximum crosswind component of 15 knots, listed in the Aircraft Flight Manual, AFM, but she only has experience with 10 knots of direct crosswind. It could be unsafe to exceed a 10-knot crosswind component without additional training. Therefore, the 10-knot crosswind experience level is Mary's personal limitation until additional training with Daniel provides her with the additional experience for flying in crosswinds that exceed 10 knots. Pilots in training must be taught that exercising good judgment begins prior to taking the controls of an aircraft. Often, pilots thoroughly check their aircraft to determine airworthiness, yet do not evaluate their own fitness for flight. Just as a checklist is used when pre-flighting an aircraft, a personal checklist based on such factors as experience, currency, and comfort level can help determine if a pilot is prepared for a particular flight. The FAA's Personal Minimums Checklist, located in Appendix D, is an excellent tool for pilots to use in self-assessment. This checklist reflects the PAVE approach to risk mitigation discussed in the previous paragraphs. Worksheets for a more in-depth risk assessment are located in the FAA/Industry Training Standards Personal and Weather Risk Assessment Guide, located online at www.faa.gov. This guide is designed to assist pilots in developing personal standardized procedures for accomplishing PIC responsibilities and in making better pre-flight and in-flight weather decisions. CFIs should stress that frequent review of the personal guide keeps the information fresh and increases a pilot's ability to recognize the conditions in which a new risk assessment should be made, a key element in the decision-making process. Situational awareness. Situational awareness is the accurate perception and understanding of all the factors and conditions within the four fundamental risk elements that affect safety before, during, and after the flight. Maintaining situational awareness requires an understanding of the relative significance of these factors and their future impact on the flight. When situationally aware, the pilot has an overview of the total operation and is not fixated on one perceived significant factor. Some of the elements inside the aircraft to be considered are the status of the aircraft systems, pilot, and passengers. In addition, an awareness of the environmental conditions of the flight, such as spatial orientation of the aircraft and its relationship to terrain, traffic, weather, and airspace, must be maintained. To maintain situational awareness, all of the skills involved in ADM are used. For example, an accurate perception of the pilot's fitness can be achieved through self-assessment and recognition of hazardous attitudes. A clear assessment of the status of navigation equipment can be obtained through workload management, and establishing a productive relationship with ATC can be accomplished by effective resource use. Obstacles to maintaining situational awareness. Many obstacles exist that can interfere with a pilot's ability to maintain situational awareness. For example, fatigue, stress, or work overload can cause the pilot to fixate on a single perceived important item rather than maintaining an overall awareness of the flight situation. A contributing factor in many accidents is a distraction, which diverts the pilot's attention from monitoring the instruments or scanning outside the aircraft. Many flight deck distractions begin as a minor problem, such as a gauge that is not reading correctly, but result in accidents as the pilot diverts attention to the perceived problem and neglects to properly control the aircraft. Fatigue, discussed as an obstacle to learning, is also an obstacle to maintaining situational awareness. It is a threat to aviation safety because it impairs alertness and performance. Figure 9-5. The term is used to describe a range of experiences from sleepy or tired to exhausted. Two major physiological phenomena create fatigue: sleep loss and circadian rhythm disruption. Fatigue is a normal response to many conditions common to flight operations because characteristics of the flight deck environment, such as low barometric pressure, humidity, noise, and vibration, make pilots susceptible to fatigue. The only effective treatment for fatigue is adequate sleep. As fatigue progresses, it is responsible for increased errors of omission, followed by errors of commission, and microsleeps, or involuntary sleep lapses lasting from a few seconds to a few minutes. For obvious reasons, errors caused by these short absences can have significant hazardous consequences in the aviation environment. Sleep-deprived pilots may not notice sleepiness or other fatigue symptoms during pre-flight and departure flight operations. Once underway and established on altitude and heading, sleepiness and other fatigue symptoms tend to manifest themselves. Extreme fatigue can cause uncontrolled and involuntary shutdown of the brain. Regardless of motivation, professionalism, or training, an individual who is extremely sleepy can lapse into sleep at any time, despite the potential consequences of inattention. There are a number of countermeasures for coping with fatigue, as shown in Figure 9-6. Figure 9-6, text. Countermeasures for coping with fatigue. Long naps, 3 to 4 hours, can restore alertness for 12 to 15 hours. Short power naps, 10 to 30 minutes, restore alertness for 3 to 4 hours. Eat high-protein meals. Drink plenty of fluids, especially water. Rotate flight tasks and converse with other crew members or passengers. Keep the flight deck temperature cool. Move/stretch in the seat, and periodically get up to walk around the aircraft if possible. Note, allow 15 to 20 minutes after awakening to become fully alert before assuming aircrew duties. End of Figure 9-6 text. Complacency presents another obstacle to maintaining situational awareness. Defined as overconfidence from repeated experience on a specific activity, complacency has been implicated as a contributing factor in numerous aviation accidents and incidents. Like fatigue, complacency reduces the pilot's effectiveness in the flight deck. However, complacency is harder to recognize than fatigue, since everything is perceived to be progressing smoothly. Highly reliable automation has been shown to induce overconfidence and complacency. This can result in a pilot following the instructions of the automation even when common sense suggests otherwise. If the pilot assumes the autopilot is doing its job, he or she does not cross-check the instruments or the aircraft's position frequently. If the autopilot fails, the pilot may not be mentally prepared to fly the aircraft manually. Instructors should be especially alert to complacency in students with significant flight experience. For example, a pilot receiving a flight review in a familiar aircraft may be prone to complacency. Advanced avionics have created a high degree of redundancy and dependability in modern aircraft systems, which can promote complacency and inattention. During flight training, the CFI should emphasize that flight operations may lead to a sense of complacency, which can threaten flight safety by reducing situational awareness. By asking about positions of other aircraft in the traffic pattern, engine instrument indications, and the aircraft's location in relation to references on a chart, the instructor can determine if the student is maintaining situational awareness. The instructor can also attempt to focus the student's attention on an imaginary problem with the communication or navigation equipment. The instructor should point out that situational awareness is not being maintained if the student diverts too much attention away from other tasks, such as controlling the aircraft or scanning for traffic. These are simple exercises that can be done throughout flight training, which help emphasize the importance of maintaining situational awareness. Operational pitfalls. There are numerous classic behavioral traps that can ensnare the unwary pilot. Pilots, particularly those with considerable experience, try to complete a flight as planned, please passengers, and meet schedules. This basic drive to demonstrate achievements can have an adverse effect on safety and can impose an unrealistic assessment of piloting skills under stressful conditions. These tendencies ultimately may bring about practices that are dangerous and sometimes illegal, and may lead to a mishap. Students develop awareness and learn to avoid many of the operational pitfalls through effective ADM training. The scenarios and examples provided by instructors during ADM instruction should involve these pitfalls. Figure 9-7. Single Pilot Resource Management, SRM. Single Pilot Resource Management, SRM, is defined as the art and science of managing all the resources, both on board the aircraft and from outside sources, available to a single pilot prior to and during flight to ensure the successful outcome of the flight. SRM includes the concepts of ADM, Risk Management, RM, Task Management, TM, Automation Management, AM, Controlled Flight into Terrain, CFIT, awareness, and Situational Awareness, SA. SRM training helps the pilot maintain situational awareness by managing the automation and associated aircraft control and navigation tasks. This enables the pilot to accurately assess and manage risk and make accurate and timely decisions. SRM is all about helping pilots learn how to gather information, analyze it, and make decisions. Although the flight is coordinated by a single person and not an onboard flight crew, The use of available resources such as air traffic control, ATC, and automated flight service station, AFSS, replicates the principles of CRM. SRM and the 5P check. SRM is about gathering information, analyzing it, and making decisions. Learning how to identify problems, analyze the information, and make informed and timely decisions is not as straightforward as the training involved in learning specific maneuvers. Learning how to judge a situation and how to think in the endless variety of situations encountered while flying out in the real world is more difficult. There is no one right answer to ADM. Rather, each pilot is expected to analyze each situation in light of experience level, personal minimums, and current physical and mental readiness level, and make his or her own decision. SRM sounds good on paper, but it requires a way for pilots to understand and use it in their daily flights. One practical application is called the 5 Ps, Figure 9-8. The 5 Ps consist of the plan, the plane, the pilot, the passengers, and the programming. Each of these areas consists of a set of challenges and opportunities that face a single pilot, and each can substantially increase or decrease the risk of successfully completing the flight based on the pilot's ability to make informed and timely decisions. The 5 Ps are used to evaluate the pilot's current situation at key decision points during the flight, or when an emergency arises. These decision points include pre-flight, pre-takeoff, hourly or at the midpoint of the flight, pre-descent, and just prior to the final approach fix, or for visual flight rules, VFR operations, just prior to entering the traffic pattern. The 5 Ps are based on the idea that the pilot has essentially 5 variables that impact his or her environment and that can cause the pilot to make a single critical decision, or several less critical decisions, that when added together can create a critical outcome. This concept stems from the belief that current decision-making models tend to be reactionary in nature. A change must occur and be detected to drive a risk management decision by the pilot. For instance, many pilots use risk management sheets that are filled out by the pilot prior to takeoff. These form a catalog of risks that may be encountered that day and turn them into numerical values. If the total exceeds a certain level, the flight is altered or canceled. Informal research shows that while these are useful documents for teaching risk factors, they are almost never used outside of formal training programs. The 5P concept is an attempt to take the information contained in those sheets and in other available models and use it. The 5P concept relies on the pilot to adopt a scheduled review of the critical variables at points in the flight where decisions are most likely to be effective. For instance, the easiest point to cancel a flight due to bad weather is before the pilot and passengers walk out the door to load the aircraft. So the first decision point is pre-flight in the flight planning room, where all the information is readily available to make a sound decision, and where communication and fixed-based operator FBO services are readily available to make alternate travel plans. The second easiest point in the flight to make a critical safety decision is just prior to takeoff. Few pilots have ever had an emergency takeoff. While the point of the 5P check is to help the pilot fly, the correct application of the 5P before takeoff is to assist in making a reasoned go, no-go decision based on all the information available. These 2 points in the process of flying are critical go, no-go points in each and every flight. The third place to review the 5 Ps is at the midpoint of the flight. Often, pilots may wait until the Automated Terminal Information Service, ATIS, is in range to check weather. Yet, at this point in the flight, many good options have already passed behind the aircraft and pilot. Additionally, fatigue and low-altitude hypoxia serve to rob the pilot of much of his or her energy by the end of a long and tiring flight day. This leads to a transition from a decision-making mode to an acceptance mode on the part of the pilot. If the flight is longer than 2 hours, the 5P check should be conducted hourly. The last two decision points are just prior to descent into the terminal area and just prior to the final approach fix, or if VFR, just prior to entering the traffic pattern, as preparations for landing commence. Most pilots execute approaches with the expectation they will land out of the approach every time. A healthier attitude requires the pilot to assume that changing conditions, the 5 P's again, will cause the pilot to divert or execute the missed approach on every approach. This keeps the pilot alert to all conditions that may increase risk and threaten the safe conduct of the flight. Diverting from cruise altitude saves fuel, allows unhurried use of the autopilot, and is less reactive in nature. Diverting from the final approach fix, while more difficult, still allows the pilot to plan and coordinate better rather than executing a futile missed approach. Let's look at a detailed discussion of each of the 5 P's. The plan. The plan can also be called the mission or the task. It contains the basic elements of cross-country planning, weather, route, fuel, publications currency, etc. The plan should be reviewed and updated several times during the course of the flight. A delayed takeoff due to maintenance, fast-moving weather, and a short-notice temporary flight restriction, TFR, may all radically alter the plan. The plan is not only about the flight plan, but also all the events that surround the flight and allow the pilot to accomplish the mission. The plan is always being updated and modified and is especially responsive to changes in the other 4 remaining P's. If for no other reason, the 5P check reminds the pilot that the day's flight plan is real life and subject to change at any time. Obviously, weather is a huge part of any plan. The addition of real-time data link weather information give the advanced avionics pilot a real advantage in inclement weather, but only if the pilot is trained to retrieve and evaluate the weather in real time without sacrificing situational awareness. And of course, weather information should drive a decision, even if that decision is to continue on the current plan. Pilots of aircraft without data link weather should get updated weather in flight through an AFSS and/or Flight Watch. The plane. Both the plan and the plane are fairly familiar to most pilots. The plane consists of the usual array of mechanical and cosmetic issues that every aircraft pilot, owner, or operator can identify. With the advent of advanced avionics, the plane has expanded to include database currency, automation status, and emergency backup systems that were unknown a few years ago. Much has been written about single-pilot IFR flight, both with and without an autopilot. While this is a personal decision, it is just that, a decision. Low IFR in a non-autopilot equipped aircraft may depend on several of the other P's to be discussed. Pilot proficiency, currency, and fatigue are among them. The pilot. Flying, especially when used for business transportation, can expose the pilot to high-altitude flying, long-distance and endurance, and more challenging weather. An advanced avionics aircraft, simply due to its advanced capabilities, can expose a pilot to even more of these stresses. The traditional "I'm safe" checklist is a good start. The combination of late night, pilot fatigue, and the effects of sustained flight above 5,000 feet may cause pilots to become less discerning, less critical of information, less decisive, and more compliant and accepting. Just as the most critical portion of the flight approaches, for instance, a night instrument approach in the weather after a 4-hour flight, the pilot's guard is down the most. The 5P process helps a pilot recognize the physiological situation at the end of the flight before takeoff and continues to update personal conditions as the flight progresses. Once risks are identified, the pilot is in an infinitely better place to make alternate plans that lessen the effect of these factors and provide a safer solution. The passengers. One of the key differences between CRM and SRM is the way passengers interact with the pilot. The pilot of a high-capability single-engine aircraft has entered into a very personal relationship with the passengers. In fact, the pilot and passengers sit within an arm's reach all of the time. The desire of the passengers to make airline connections or important business meetings enters easily into this pilot's decision-making loop. Done in a healthy and open way, this can be a positive factor. Consider a flight to Dulles Airport, and the passengers, both close friends and business partners, need to get to Washington, D.C. for an important meeting. The weather is VFR all the way to Southern Virginia, then turns to low IFR as the pilot approaches Dulles. A pilot employing the 5P approach might consider reserving a rental car at an airport in northern North Carolina or Southern Virginia to coincide with a refueling stop. Thus, the passengers have a way to get to Washington, and the pilot has an out to avoid being pressured into continuing the flight if the conditions do not improve. Passengers can also be pilots. If no one is designated as pilot in command, PIC, and unplanned circumstances arise, the decision-making styles of several self-confident pilots may conflict. Pilots also need to understand that non-pilots may not understand the level of risk involved in the flight. There is an element of risk in every flight. That is why SRM calls it risk management, not risk elimination. While a pilot may feel comfortable with the risk present in a night IFR flight, the passengers may not. A pilot employing SRM should ensure the passengers are involved in the decision-making and given tasks and duties to keep them busy and involved. If, upon a factual description of the risks present, the passengers decide to buy an airline ticket or rent a car, then a good decision has generally been made. This discussion also allows the pilot to move past what he or she thinks the passengers want to do and find out what they actually want to do. This removes self-induced pressure from the pilot. The programming. The advanced avionics aircraft adds an entirely new dimension to the way general aviation aircraft are flown. The electronic instrument displays, GPS, and autopilot reduce pilot workload and increase pilot situational awareness. While programming and operation of these devices are fairly simple and straightforward, unlike the analog instruments they replace, they tend to capture the pilot's attention and hold it for long periods of time. To avoid this phenomenon, the pilot should plan in advance when and where programming for approaches, route changes, and airport information gathering should be accomplished, as well as times it should not. Pilot familiarity with the equipment, the route, and the local air traffic control environment, and personal capabilities vis-a-vis the automation should drive when, where, and how the automation is programmed and used. The pilot should also consider what his or her capabilities are in response to last-minute changes of the approach and the reprogramming required, and ability to make large-scale changes, a reroute for instance, while hand-flying the aircraft. Since formats are not standardized, simply moving from one manufacturer's equipment to another should give the pilot pause and require more conservative planning and decisions. The SRM process is simple. At least 5 times before and during the flight, the pilot should review and consider plan, the plane, the pilot, the passengers, and the programming, and make the appropriate decision required by the current situation. It is often said that failure to make a decision is a decision. Under SRM and the 5 Ps, even the decision to make no changes to the current plan is made through careful consideration of all the risk factors present. Information management. The volume of information presented in aviation training is enormous, but part of the process of good SRM is a continuous flow of information in and actions out. How a student manages the flow of information definitely has an effect on the relative success or failure of each and every flight, because proper information contributes to valid decisions. SBT plays an important part in teaching the student how to gather pertinent information from all available sources, make appropriate decisions, and assess the actions taken. For a transitioning pilot, the primary flight display, PFD, multifunction display, MFD, and GPS/very high frequency, VHF navigator screens seem to offer too much information presented in colorful menus and submenus. In fact, the student may be overwhelmed and unable to find a specific piece of information. The first critical information management skill for flying with advanced avionics is to understand the system at a conceptual level. Remembering how the system is organized helps the pilot manage the available information. Simulation software and books on the specific system used are of great value in further understanding for both the CFI and the student. Another information management skill is reading. The best strategy for assessing and managing the available information from PFD to navigational charts is to stop, look, and read. The goal is for the student to learn how to monitor, manage, and prioritize the information flow to accomplish specific tasks. Task management, TM. Task management, TM, a significant factor in flight safety, is the process by which pilots manage the many concurrent tasks that must be performed to safely and efficiently fly a modern aircraft. A task is a function performed by a human as opposed to one performed by a machine, e.g., setting the target heading in the autopilot. The flight deck is an environment in which potentially many important tasks compete for pilot attention at a given time. TM determines which of perhaps many concurrent tasks the pilots attend to at any particular point in time. More specifically, TM entails initiation of new tasks, monitoring of ongoing tasks to determine their status, prioritization of tasks based on their importance, status, urgency, and other factors, allocation of human and machine resources to high-priority tasks, interruption and subsequent resumption of lower-priority tasks, and termination of tasks that are completed or no longer relevant. Humans have a limited capacity for information. Once information flow exceeds a person's ability to mentally process the information, any additional information becomes unattended or displaces other tasks and information already being processed. Once the information flow reaches its limit, two alternatives exist: shed the unimportant tasks or perform all tasks at less than optimal level. Like an electrical circuit being overloaded, either the consumption must be reduced or a circuit failure is experienced. Once again, SBT helps the student learn how to effectively manage tasks and properly prioritize them. Automation management. Automation management is the demonstrated ability to control and navigate an aircraft by means of the automated systems installed in the aircraft. One of the most important concepts of automation management is knowing when to use it and when not to use it. Ideally, the goal of the flight instructor is to train the student until he or she has learned how to perform PTS maneuvers and procedures in the aircraft using all the available automation and/or the autopilot. However, the flight instructor must ensure the student also knows how to turn everything off and hand fly the maneuver when the safety of the flight is threatened. Advanced avionics offer multiple levels of automation, from strictly manual flight to highly automated flight. No one level of automation is appropriate for all flight situations. But in order to avoid potentially dangerous distractions when flying with advanced avionics, the student must know how to manage the course indicator, the navigation source, and the autopilot. It is important for a student to know the peculiarities of the particular automated system being used. This ensures the student knows what to expect, how to monitor for proper operation, and promptly take appropriate action if the system does not perform as expected. At the most basic level, managing the autopilot means knowing at all times which modes are engaged and which modes are armed to engage. The student needs to verify that armed functions, e.g., navigation tracking or altitude capture, engage at the appropriate time. Automation management is a good place to practice the call-out technique, especially after arming the system to make a change in course or altitude. Teaching decision-making skills. When instructor pilots discuss system safety, they generally worry about the loss of traditional stick and rudder skills. The fear is that emphasis on items such as risk management, ADM, SRM, and situational awareness detracts from the training necessary in developing safe pilots. It is important to understand that system safety flight training occurs in 3 phases. First, there are the traditional stick and rudder maneuvers. In order to apply the critical thinking skills that are to follow, pilots must first have a high degree of confidence in their ability to fly the aircraft. Next, the tenets of system safety are introduced into the training environment as students begin to learn how to best identify hazards, manage risk, and use all available resources to make each flight as safe as possible. This can be accomplished through scenarios that emphasize the skill sets being taught. Finally, the student is introduced to more complex scenarios, demanding focus on several safety of flight issues. Thus, scenarios should start out rather simply, then progress in complexity and intensity as the student can handle the learning load. A traditional stick and rudder maneuver, such as short field landings, can be used to illustrate how ADM and risk management can be incorporated into instruction. In Phase 1, the initial focus is on developing the stick and rudder skills required to execute this operation safely. These include power and airspeed management, aircraft configuration, placement in the pattern, wind correction, determining the proper aim point and sight picture, etc. By emphasizing these points through repetition and practice, a student eventually acquires the skills needed to execute a short field landing. Phase 2 introduces the many factors that come into play when performing a short field landing, which include runway conditions, no-flap landings, airport obstructions, and rejected landings. The introduction of such items need not increase training times. In fact, all of the hazards or considerations referenced in the short field landing lesson plan may be discussed in detail during the ground portion of the instructional program. For example, if training has been conducted at an airport that enjoys an obstruction-free 6,000-foot runway, consider the implications of operating the same aircraft out of an 1,800-foot strip with an obstruction off the departure end. Add to that additional considerations, such as operating the aircraft at close to its maximum gross weight under conditions of high-density altitude, and now a single training scenario has several layers of complexity. The ensuing discussion provides a valuable training exercise, and it comes with little additional ground and no added flight training. Finally, Phase 3 takes the previously discussed hazards, risks, and considerations and incorporates them into a complex scenario. This forces a student to consider not only a specific lesson item, in this case short field landings, but also requires that it be viewed in the greater context of the overall flight. For example, on a cross-country flight, the student is presented with a realistic distraction, perhaps the illness of a passenger. This forces a diversion to an alternate for which the student has not planned. The new destination airport has 2 runways, the longest of which is closed due to construction. The remaining runway is short, but while less than ideal, should prove suitable for landing. However, upon entering the pattern, the student finds the electrically driven flaps do not extend. The student must consider whether to press on and attempt the landing or proceed to a secondary alternate. If he or she decides to go forward and attempt the landing, this proves an excellent time to test the requisite stick and rudder skills. If the student decides to proceed to a second alternate, this opens new training opportunities. Proceeding further tests cross-country skills, such as navigation, communication, management of a passenger in distress, as well as the other tasks associated with simply flying the aircraft. The outlined methodology simply takes a series of seemingly unrelated tasks and scripts them into a training exercise requiring both mechanical and cognitive skills to complete it successfully. SBT helps the flight instructor effectively teach ADM and risk management. The what, why, and how of SBT has been discussed extensively throughout this handbook. In teaching ADM, it is important to remember the learning objective is for the student to exercise sound judgment and make good decisions. Thus, the flight instructor must be ready to turn the responsibility for planning and execution of the flight over to the student as soon as possible. Although the flight instructor continues to demonstrate and instruct skill maneuvers, When the student begins to make decisions, the flight instructor should revert to the role of mentor and/or learning facilitator. The flight instructor is an integral part of the system's approach to training and is crucial to the implementation of an SBT program, which underlies the teaching of ADM. Remember, for SBT instruction to be effective, it is vital the flight instructor and the student establish the following information: scenario destinations, desired student learning outcomes, desired level of student performance, possible in-flight scenario changes. It is also important for the flight instructor to remember that a good scenario is not a test, will not have a single correct answer, does not offer an obvious answer, engages all three learning domains, is interactive, should not promote errors, should promote situational awareness and opportunities for decision-making, requires time-pressured decisions. The flight instructor should make the situation as realistic as possible. This means the student knows where he or she is going and what transpires on the flight. While the actual flight may deviate from the original plan, it allows the student to be placed in a realistic scenario. The student will plan the flight to include route, destinations, weather, NOTAMs, possible emergency procedures. Since the scenarios may have several good outcomes and a few poor ones, the flight instructor should understand in advance which outcomes are positive and/or negative and give the student the freedom to make both good and poor decisions. This does not mean that the student should be allowed to make an unsafe decision or commit an unsafe act. However, it does allow the students to make decisions that fit their experience level and result in positive outcomes. Teaching decision-making skills has become an integral part of flight training. The word decision is used several times in each PTS, and applicants are judged on their ability to make a decision as well as their ability to perform a task. Thus, it is important for CFIs to remember that decision-making is a component of the PTS. Assessing SRM skills. The student's performance is often assessed only on a technical level. The instructor determines whether maneuvers are technically accurate and that procedures are performed in the right order. In SRM assessment, instructors must learn to assess students on a different level. How did the student arrive at a particular decision? What resources were used? Was risk assessed accurately when a go, no-go decision was made? Did the student maintain situational awareness in the traffic pattern? Was workload managed effectively during a cross-country flight? How does the student handle stress and fatigue? Instructors should continually evaluate student decision-making ability and offer suggestions for improvement. It is not always necessary to present complex situations which require detailed analysis. By allowing students to make decisions about typical issues as they arise throughout the course of training, such as their fitness to fly, weather conditions, and equipment problems, instructors can address effective decision-making and allow students to develop judgment skills. For example, when a discrepancy is found during pre-flight inspection, the student should be allowed to initially determine the action to be taken. Then, the effectiveness of the student's choice and other options that may be available can be discussed. Opportunities for improving decision-making abilities occur often during training. If the tower offers the student a runway that requires landing with a tailwind in order to expedite traffic, the student can be directed to assess the risks involved and asked to present alternative actions to be taken. Perhaps the most frequent choice that has to be made during flight training is the go, no-go decision based on weather. While the final choice to fly lies with the instructor, students can be required to assess the weather prior to each flight and make a go, no-go determination. In addition, instructors should utilize SBT to create lessons that are specifically designed to test whether students are applying SRM skills. Planning a flight lesson in which the student is presented with simulated emergencies, a heavy workload, or other operational problems can be valuable in assessing the student's judgment and decision-making skills. During the flight, student performance can be evaluated for workload and/or stress management. As discussed in Chapter 5, SRM grades are based on these four components. Explain. The student can verbally identify, describe, and understand the risks inherent in the flight scenario. The student needs to be prompted to identify risks and make decisions. Practice. The student is able to identify, understand, and apply SRM principles to the actual flight situation. Coaching, instruction, and/or assistance from the CFI quickly corrects minor deviations and errors identified by the CFI. The student is an active decision maker. Manage, decide. The student can correctly gather the most important data available both within and outside the flight deck, identify possible courses of action, evaluate the risk inherent in each course of action, and make the appropriate decision. Instructor intervention is not required for the safe completion of the flight. Not observed. Any event not accomplished or required. Post-flight, collaborative assessment or learner-centered grading, LCG, also discussed in Chapter 5, is a vital component of assessing a student's SRM skills. As a reminder, collaborative assessment includes two parts: learner self-assessment and a detailed assessment by the flight instructor. The purpose of the self-assessment is to stimulate growth in the student's thought processes and, in turn, behaviors. The self-assessment is followed by an in-depth discussion between the flight instructor and the student, which compares the CFI's assessment to the student's self-assessment. An important element of SRM skill assessment is that the CFI provides a clear picture of the progress the student is making during the training. Grading should also be progressive. During each flight, the student should achieve a new level of learning. For Flight 1, the automation management area might be a describe item. By Flight 3, it would be a practice item, and by Flight 5, manage decide item. Chapter Summary. This chapter introduced aviation instructors to the underlying concepts of safety risk management, which the FAA is integrating into all levels of the aviation community.